we are going to talk a little bit more about that characteristic equation on this last page. Specifically, geometric and algebraic multiplicity of an eigenvalue. I'm confident that we have an idea of what algebraic multiplicity is. It's just a number, it's the number of times that the zero of a polynomial would show up as an answer. So, you've probably worked with zeros of, like multiplicity 2 or multiplicity 3, and, looked at the if of graph at that 0 on the x-axis. But we will include that. However, in addition to it, we will discuss what's called geometric multiplicity. So to start this out, it says the factors of the characteristic polynomial from characteristic equation does have some meaningful implications. So here's a couple of definitions where I'll define geometric and algebraic multiplicity. It says if lambda sub 0, not the Mortal Kombat way, is an eigenvalue of a square matrix, then the dimension, i.e. the number of basis vectors of the corresponding eigenspace, is called the geometric multiplicity. Okay, so geometric multiplicity refers to the dimension of the eigenspace associated with the eigenvalue. You'll probably hear me say it as geomult, though, so short for geometric multiplicity. The number of times that the factor lambda minus lambda sub 0 is a factor of the characteristic polynomial is called the algebraic multiplicity. So algebraic multiplicity refers to the factor of the characteristic polynomial. So the number of times factor lambda minus that number is a factor of the characteristic polynomial. And there's some connection between these two types of multiplicity. For each eigenvalue of the matrix A, the geometric multiplicity will always be less than or equal to the algebraic multiplicity. In the case where the geometric multiplicity is less than the algebraic multiplicity, the matrix A is not diagonalizable. And that would be because you wouldn't have enough eigenspace basis vectors to form the matrix P. However, if the matrix A is diagonalizable, then what you would find, the geometric multiplicity is equal to the algebraic multiplicity of the eigenvalue. Right, this would guarantee that we have enough basis vectors to populate a square matrix. One thing I do want to note is that the geometric multiplicity, I'll write this as geomult, will never equal 0. Likewise, the algebraic multiplication, or multiplicity I should say, will not equal 0. Of the two, I think this is a more important fact. If the geometric multiplicity were to equal 0, then our eigenspace would just be the 0 vector, which by definition we're excluding that. So the geometric multiplicity as well as the algebraic multiplicity will always be greater than 0, and they'll each be integers. With that, we're on to our last example, where we're provided a partially factored form of a characteristic equation. And with that, we want to find the size of the matrix, is one part, and then the possible dimensions of eigenspaces. Okay. Now, to find the size of the matrix, we have to determine the degree of the characteristic polynomial. Okay, so the size of the matrix is equal to the degree of the characteristic polynomial. And looking at the expression on the left-hand side, what would the degree of this polynomial be? Well, one thing that we could do is maybe distribute lambda square into each of these. And we'd have lambda to the fourth minus 5 lambda cubed minus 6 lambda squared equals 0. And if this were in terms of x, we would find that the degree of this polynomial is 4. Well, keep in mind that lambda is basically a variable, a bougie variable. And since the highest power is 4, that would be our degree. Okay, so the degree equals 4, which means that the size of the matrix would be 4 by 4. If it were 3 by 3, then our characteristic equation would have degree 3, because there would be 3 factors of lambda minus something being multiplied out. And if it were degree 5, there would be 5 factors of lambda minus something we'd have to multiply out. So the only way the degree could be 4 is if the size of the matrix is 4 by 4. So that's the first. Second part, I like a lot better. It's kind of fun in my opinion. So I'm going to write out the equation that they provided us. And I'm going to factor the left-hand side as much as possible. All right? I'm even going to rewrite lambda squared as lambda times lambda. I know, rebel, right? You can factor what's in parentheses as lambda minus 6 times lambda plus 1. And we will want to solve for lambda so that we know what the eigenvalues of the matrix are. And by having everything completely factored, given the lambda squared, we can get a sense of multiplicities, the algebraic multiplicities associated with each eigenvalue. So if you use the zero product property to set each factor equal to 0, we'll have a couple of copies of lambda equals 0. We'll then have lambda equals 6 and lambda equals -1. So you'll notice that lambda equals 0 showed up twice as an answer. So what would the multiplicity be, namely the algebraic multiplicity? Yep. Lambda equals 6 only showed up once, so it would have an algebraic multiplicity of 1. Likewise, -1 would have a multiplicity of 1 since it only showed up once as an eigenvalue. Now for the geometric multiplicity, what I'd like to do is construct a table. So in this table, there are going to be 3 rows and 3 columns. And let's see. Yep, in the first column, I'm just going to plot the eigenvalues going from smallest to largest. So the smallest of the eigenvalues was -1. So I'll write lambda equals -1. Then we have lambda 0. Then we have lambda equals 6. In each of the columns, we're going to log down first the algebraic multiplicity, or algmult, and then the geomult, and then we'll write out the possible dimensions of the eigenspaces. So I'll just write it as B or M ES, ES for eigenspace. the algebraic multiplicity of -1. 0 had algebraic multiplicity of 2, and then 6 had algebraic multiplicity of 1. Now, keeping in mind that the geometric multiplicity is always less than or equal to the algebraic multiplicity, as well as the fact that the geometric multiplicity cannot equal 0, the geometric multiplicity for lambda equals -1 is going to be 1. Okay, because that's the only positive integer that's less than or equal to 1. For the geometric multiplicity of lambda equals 0, though, there are two possibilities for the geomult. There could be, one basis vector for lambda equals 0, or there could be 2, since those two numbers are less than or equal to 2. And then for lambda equals 6, what do you think the geometric multiplicity is going to be? Right. So remember, the geometric multiplicity would tell you the number of basis vectors for the corresponding eigenvalue. So with lambda equals -1, since the algebraic multiplicity is equal to the geometric multiplicity, we would be guaranteed one basis vector for the eigenspace for lambda equals -1. So the dimension of the eigenspace would be 1. As for lambda equals 0, it's kind of a toss-up until we actually hunt down the basis vectors. So there's a possibility that the basis for the eigenspace just has one basis vector, in which case the dimension would be 1. Or, it might be the situation where there are two basis vectors for lambda equals 0. So the best we can say about the dimension is that it's going to either be 1 or 2, but nothing else. And then since the algmult equals the geomult for lambda equals 6, then we would be guaranteed one basis for that. All right, so to add a little more detail to this, if we were to find basis for lambda equals -1, then the basis would have one eigenvector. If we were to hunt down a basis for lambda equals 0, then the basis might consist of one eigenvector, or might consist of two eigenvectors, which I'll separate them and write them as P and Q. And then for the last eigenvalue, we're guaranteed a basis of just one eigenvector. Now, this matrix A would be diagonalizable if and only if this is an eigenvector basis, this is a basis for lambda equals 0, and this is the basis for lambda equals. And the reason for that is because the matrix is 4 by 4. So if you want to find a matrix P, then we would need 4 eigenvectors in order to do that. Should the geometric multiplicity of lambda equals 0 be 1, then there wouldn't be enough eigenvectors to construct a matrix P. Does that all make sense? Are there any questions about anything that we went over today?